Good evening and welcome into the Science Files. I'm Madeline Rowe, and this evening we're going to open one of the largest files in cosmology, a question so simple in its wording that it can be mistaken for a child's question, and so difficult in its evidence that even the best instruments humanity ever built could not close it completely. Is the universe infinite? And if it is not, how would we ever know? We'll follow what can actually be measured: the observable universe, the age of the light reaching us, the cosmic microwave background, the geometry of space, the galaxy surveys that use ancient sound waves as rulers, and the strange possibility that space could be finite without having an edge. And if you enjoy these calm, evidence-backed case files, please subscribe, and there'll be another one waiting for you soon. The file on my desk is thinner than a question this large should be. That is the first honest thing about it. The title has been typed in faded black ink, then corrected by hand, then corrected again. Is the universe infinite? Beneath that, a smaller line reads, "What cosmology can actually measure?" The folder has been sealed with an old archival clasp, tarnished by time, but still holding. When I open it, several kinds of evidence slide into the light. Sky maps, power spectra, distance ladders, survey catalogues, sketches of curved space, and a set of diagrams where circles on the microwave sky have been marked, compared, and crossed out. I arranged them carefully, not in the order they were found, but in the order the question requires. First, the light that reaches us, then the geometry it crossed, then the blank region beyond the measurements. Back in my office, which sits beneath the ship's forward observation dome, the hull above me curves into a dark pane of glass. Beyond it, the stars do what stars always do from this distance. They appear still. That stillness is an illusion made by scale. The ship is moving. The stars are moving. The space between galaxies has been expanding for nearly the entire history of the universe. On the desk, the archive projects a sphere around a small marker labelled here. It is not a wall, it is a limit. Inside the sphere, the projection is detailed. Galaxies, clusters, filaments, faint microwave texture left from the young universe. Outside it, the display does not draw an edge, it simply fades. That fading is where this case begins. There are questions that fail because the evidence is too poor. There are others that survive because the evidence is very good, but not the kind that can answer everything. The size of the whole universe belongs to the second class. Humanity measured the universe with astonishing precision. It measured the age of ancient light. It measured the expansion rate. It measured the bending of space-time through gravity, the clustering of galaxies, the slight temperature variations in radiation that had crossed almost all observable history. It learned that the region we can see is vast, old, and close to spatially flat. But the total universe may be larger than the region that can ever send light to us. It may be infinite, it may be finite, and wrapped in a way too large for the evidence to reveal. It may be finite in a shape that leaves no simple visual border and no comforting outside. The first piece of discipline is to separate the observable universe from the universe. They are often treated as the same thing in casual speech. They are not the same in cosmology. The observable universe is the region from which light, or other signals has had time to reach us since the hot early phase of cosmic history. It is not a shell around Earth in any special physical sense. Every observer in every galaxy has a surrounding observable universe centered on their own world line, because every observer has a past light cone. The boundary is made by time, light speed, and expansion. It is a boundary of information. If a galaxy lies beyond our particle horizon, its light has not had enough time to reach us since the beginning of the hot Big Bang phase. That does not mean the galaxy is unreal. It means it is outside our record. A careful archive must treat absence of evidence in that region differently from evidence of absence. There are parts of the whole that may never enter the file. The phrase observable universe also carries a subtle numerical surprise. The universe is about 13.8 billion years old, but the radius of the observable universe is not 13.8 billion light years. The most distant matter whose ancient light reaches us today is now much farther away in present-day co-moving distance, roughly 46 billion light years. This is possible because space has expanded while the light was travelling. The photons did not cross a static arena. They moved through a metric that changed beneath them. That distinction caused confusion for a long time, and it still does. In the archive, one of the early diagrams shows a past light cone drawn through a universe whose scale factor grows with time. Near the centre is the observer. Around it is the Hubble sphere, the distance at which recession speed, as described by Hubble's law in an expanding universe, equals the speed of light. A common mistake is to treat that sphere as a hard observational horizon. It is not. Light can reach us from galaxies that are now receding faster than light, and in a general relativistic universe that does not violate the local rule that light travels at sea. The galaxy is not flying through local space faster than a beam of light passing beside it. Space itself is changing the relationship between distant co-moving points. This is a place where language becomes dangerous. Recession speed in cosmology is not the same as a rocket passing through a local laboratory. Special relativity governs local motion. General relativity gives the larger description of an expanding spacetime. When the separation between two faraway co-moving galaxies increases faster than light because the scale factor changes, no signal is outrunning a local photon in its own neighbourhood. The rule survives. The intuitive picture breaks. In the long corridor outside the research bay, the ship gives me a useful model. Though like all models, it has to be handled with care. There are pressure doors at intervals along the corridor. A person walking beside me could never outrun a light pulse in that corridor. But if the corridor itself were being stretched between us and a far door, the distance to the far door could increase while the light still moved locally at its ordinary speed. A ship corridor cannot really do this. Space-time can. The analogy is only a handrail, not the structure itself. The earliest cosmologists did not begin with these horizons. They began with the sky, with geometry, and with a very old desire to know whether space has an end. Ancient arguments about the universe often mixed observation with philosophy, because the available evidence was thin. The fixed stars looked like a sphere. The wandering planets crossed it. The Earth was once placed at the centre of a finite cosmic architecture, not because the universe had been measured, but because that arrangement gave the night sky an order the mind could hold. Then telescopes widened the file. Stars became suns. Nebulae became galaxies. The Milky Way lost its claim to be the whole. Newtonian gravity made an infinite universe difficult in one way and attractive in another. If matter fills all space, every direction pulls. If matter has an edge, the edge has consequences. Philosophers and physicists wrestled with the problem before they had the evidence to settle it. A static, eternal, infinite universe also carried the old difficulty of the dark night sky. If stars had filled infinite space forever, every line of sight ought to end on a stellar surface. The fact that the sky is dark was a clue, but not a complete explanation until expansion, finite stellar lifetimes, and cosmic history entered the case. Einstein's general relativity changed the question. Space was no longer a passive container. It had geometry. Matter and energy shaped space-time, and space-time guided matter and light. Einstein's first cosmological model was static and spatially closed, a finite universe without an edge. Then Friedmann and Lemaitre found expanding solutions in the equations. Hubble's observations of galaxy redshifts and distances made expansion an observational fact. The question of infinity moved from metaphysics into measurement. In the archive vault, the older records are stored on metal wafers in drawers that open with a soft mechanical resistance. The drawer labelled Geometry contains 3 engraved surfaces. One is spherical, one saddle-shaped, one flat. They are only 2-dimensional teaching surfaces, but they stand for 3 possible spatial geometries in the simplified Friedmann, Lemaitre, Robertson-Walker models: positive curvature, negative curvature, and zero curvature. In a positively curved space, large triangles can have angles adding to more than 180 degrees. In a negatively curved space, less than 180. In a flat Euclidean space, exactly 180. Cosmology cannot stretch measuring rods across the entire universe, so it uses light, standard rulers, and the relics of the early universe. The curvature parameter is usually written as omega k. If omega k is 0, the large-scale spatial geometry is flat. If it is positive or negative, space has open or closed curvature depending on the convention being used. The sign conventions can be annoying. The physical idea is simpler than the notation. Curvature changes the relationship between physical sizes, angles on the sky, and distances. A known ruler at a known distance appears at a different angular size depending on the geometry through which its light has travelled. The cosmic microwave background gave humanity one of the most powerful rulers it ever found. It is ancient light, released when the universe cooled enough for electrons and nuclei to combine into neutral atoms, about 380,000 years after the hot early phase. Before that, photons scattered constantly off free electrons in a hot plasma. After recombination, the photons travelled freely. They arrive now as a nearly uniform bath of microwave radiation, cooled by expansion to a temperature of about 2.7 Kelvin, with tiny temperature variations across the sky. Those variations are not random smudges. They preserve information about sound waves in the early plasma, about the density of ordinary matter, dark matter, radiation, and the geometry of the path between the last scattering surface and us. When the Planck satellite measured the microwave sky, it was not taking a photograph of an outer edge. It was mapping the surface from which the oldest freely travelling light could reach us. In the holographic evidence bay, the CMB appears as a sphere of faint mottled colour around the room. The projection has no single privileged centre except the observer reconstructed inside it. If I move the observer marker to another galaxy, that galaxy receives its own sphere. This is one reason the CMB is easy to misunderstand. It looks like a shell around us, but it is not a shell in space with Earth or the ship at the center of creation. It is a shell in observation. It is where our past light cone intersects the epoch when the universe became transparent. The archive overlays the CMB sphere with acoustic peaks. These peaks are not peaks in a mountain range. They are features in the angular power spectrum, a way of describing how much temperature variation appears at different angular scales on the sky. The first acoustic peak gives a measure of a characteristic scale at recombination, projected through the geometry of the universe. If space were strongly curved, that scale would appear shifted. Planck measured the angular acoustic scale with extraordinary precision. Combined with other data, especially baryon acoustic oscillations, it found the observable universe to be consistent with spatial flatness. That result is often flattened into the phrase, "the universe is flat." The file does not allow that sentence to stand alone. The better statement is more careful. Within the standard cosmological model and the data combinations used, the spatial curvature of the observable universe is constrained to be very close to zero. Planck 2018, combined with baryon acoustic oscillation measurements, gave a curvature constraint consistent with flatness, with omega k around 0.001 plus or minus 0.002. The uncertainty is small, the implication is strong, but it is still a measurement inside a model, made from within one observable region. Baryon acoustic oscillations deserve their own place in the file because they give the CMB a later universe companion. In the young universe, ordinary matter and radiation were coupled. Pressure waves travelled through that plasma. When photons decoupled, the waves left a preferred scale in the distribution of matter. Billions of years later, galaxy surveys found that galaxies are very slightly more likely to be separated by that characteristic scale than by nearby scales. The pattern is faint, but across enough galaxies it becomes measurable. At the cartography table, I set down two rulers. One comes from the CMB, one comes from galaxy clustering. They are not made of metal, they are statistical rulers carved into the distribution of matter and light. The CMB ruler reaches back to recombination. The BAO ruler shows how that same early universe physics echoes in the later distribution of galaxies and quasars. Galaxy surveys such as DESI measure the BAO feature across redshift. Across the sky, the scale constrains distance. Along the line of sight, it constrains the expansion rate. Together with the CMB, BAO measurements help break geometric degeneracies that CMB data alone cannot fully break. A degeneracy is not a defect in an instrument. It is a situation where different combinations of parameters can produce similar observations. The CMB is powerful, but some changes in curvature, dark energy, and expansion history can partially mimic one another in the angular scale of features. BAO helps by adding distance measurements at later cosmic times. It gives the map depth. It says not only what the early ruler looked like on the ancient sky, but how the expansion history carried related rulers into the era of galaxies. This is how the case accumulates strength, not by a single dramatic measurement, by cross-checks. The CMB constrains the early universe. BAO surveys constrain the distance redshift relation. Supernovae measure relative distances through standardizable candles. gravitational lensing traces matter structure. Each method has assumptions and systematics, but the broad result remains. On the largest measured scales, the observable universe is homogeneous, isotropic, expanding, and close to spatially flat. The words homogeneous and isotropic need careful handling. Homogeneous means that, on sufficiently large scales, the universe has roughly the same average properties from place to place. Isotropic means that it looks roughly the same in every direction. The CMB strongly supports isotropy, with tiny anisotropies that seeded later structure. Galaxy surveys support large-scale homogeneity, though only above large enough scales. The universe is not smooth on the scale of a galaxy, or a cluster, or a filament. It becomes statistically smooth when the map is blurred over enormous distances. Planck's statistical studies of the CMB found excellent agreement with the Gaussian predictions of the standard lambda-cold dark matter model over much of the data. They also confirmed some large-angle anomalies previously seen in temperature maps. These anomalies include features such as low power at the largest angular scales and alignments that have attracted attention for years. But attention is not the same as proof. Their statistical significance is modest, and some tests are vulnerable to the look elsewhere effect, where patterns become more interesting after one has already noticed them. Polarization data can help check whether the temperature anomalies correspond to something physical, but current evidence does not turn them into a clear detection of new global structure. That caution matters because anomalies can tempt a writer toward a more dramatic story than the data support. The better story is also more interesting. The universe left hints that are mostly consistent with the standard model, and a few large-scale features that invite testing. Scientists looked for departures from ordinary statistical isotropy. They looked for topology. They looked for non-Gaussianity. The standard model held up very well. The unanswered question did not disappear. It became more sharply defined. I leave the evidence bay and pass through the long corridor that runs below the observation dome. The ship's lights are dim here. A line of status indicators moves along the wall, green, green, green. Then a single amber light where an old sensor reports a harmless uncertainty. The corridor curves gently. From inside it, the curve is almost imperceptible. You need a plan of the ship to know its larger shape. That is one of the first lessons of curvature. Local measurements may not reveal global form unless the curvature is large enough, or the path is long enough, or the instruments are precise enough. A small creature walking on Earth can treat the ground beneath its feet as flat. Survey enough land, track ships against horizons, watch shadows at different latitudes, or fly into orbit, and the curvature becomes undeniable. Cosmology has the same problem with a crueler scale. We cannot step outside the universe to look at it. We cannot build a ruler longer than the observable universe. We infer geometry from inside the system. When current observations say the observable universe is nearly flat, they are saying that any curvature radius, if curvature exists, is very large compared with the scale we can measure. A flat-looking patch does not prove an infinite plane. A small region on a huge sphere also looks flat. A universe with a curvature radius far beyond our horizon could appear indistinguishable from flat within the region available to us. This is where the question of infinity divides into geometry and topology. Geometry tells us about local and large-scale curvature. Topology tells us how space is connected. two spaces can share the same local geometry and have different global forms. A flat Euclidean space can be infinite, extending without bound in every direction. A flat 3 torus can be finite, with paths that wrap around and return, while every local measurement still behaves as though space were Euclidean. The difference is not in the small geometry under one's feet. It is in the global identification of points. The archive holds a teaching diagram for this, worn at the edges from old use. It begins with a square. If the left edge is identified with the right edge and the top edge with the bottom, a traveller leaving one side re-enters from the opposite side. On the page, the square becomes a 2-dimensional torus. In 3 dimensions, the analogy becomes harder to picture, but the mathematics is clear. A finite flat universe can have opposite faces of a fundamental domain identified. There are no walls. There is no border where a traveller strikes the end of existence. The topology changes the paths through space. A phrase like wraparound universe can sound playful, so the file avoids leaning on it too heavily. The physical idea is more sober. In a multiply connected universe, there are paths through space that cannot be continuously shrunk to a point. Light from the same object could, in principle, reach an observer by more than one route. A galaxy might appear in multiple directions as ghost images of itself, though at different ages, because the light paths would have different lengths. The cosmic microwave background might show repeated patterns if the topology scale were small enough. This is one of the most important corrections in the episode. Flat does not automatically mean infinite. Positive curvature in a simply connected universe implies finite spatial volume in the standard models. Negative or zero curvature in the simplest topology is infinite, but general relativity does not force the simplest topology. The field equations describe local geometry. They do not by themselves choose the global connectedness of space. In the central archive chamber, this distinction is engraved into the display as 2 separate fields, curvature and topology. But the first field contains measured constraints. The second contains possibilities, many of them only partly tested. The chamber is circular, but if one walks far enough along its outer gallery, one returns to the same door. The room is finite without having a useful edge. It is a modest architectural trick, but it gives the mind a place to rest while considering a more abstract one. Cosmic topology became observationally serious because of the CMB. If the universe were finite and smaller than the diameter of the last scattering surface in a detectable way, the surface of last scattering could intersect with copies of itself in the covering space. The intersection of 2 spheres is a circle. That is the origin of the famous matched circles idea. If we were seeing the same physical region of the early universe in 2 different directions, then 2 circles on the microwave sky might carry matching temperature patterns, possibly with reversed orientation or phase, depending on the topology. There is something beautifully restrained about that test. It doesn't ask whether infinity feels plausible. It asks whether the oldest light contains repeated evidence. The microwave background becomes a forensic surface. Each ring is examined, rotated, compared. Are the fluctuations along one circle the same as along another? Are they correlated strongly enough to overcome noise, foreground contamination, and the statistical accidents of a single sky? The Planck collaboration searched for these signatures with temperature and polarization data. It also used likelihood methods for specific topologies, including cubic torus and slab models. The result was negative. No compact topology was detected below the diameter of the last scattering surface for the models tested. For a cubic torus, Planck placed a lower limit on the radius of the largest sphere that could fit inside the fundamental domain, roughly 0.97 times the comoving distance to recombination. For a slab topology, the corresponding limit was lower, around 0.56 times that distance, reflecting the different geometry of the model and the sensitivity of the search. Those numbers are not meant to be memorized by the listener as a table. Their meaning is enough. Planck did not find evidence that the observable universe is a small repeating cell. If space wraps around on scales below or near the last scattering diameter in the simplest ways examined, it should have left patterns that Planck did not see. That is a genuine constraint. It rules out some tempting finite models. It doesn't rule out all finite universes. The reason is parameter space. Even among flat compact topologies, there are multiple possible forms, with different lengths, twists, orientations, and degrees of freedom. The simplest 3 torus is only the easiest room in a much larger building. Some topologies might be too large to create matched circles. Some might create correlations without obvious circles. Some might produce signals that are computationally difficult to search for across all orientations and parameters. The absence of a familiar signature is evidence against the models that would produce that signature at detectable strength. It is not a certificate of infinity. I stop at the cartography table again. The projection now shows 3 maps of the same corridor. In one, the corridor runs forever. In another, it curves back on itself after a distance too large to walk within a lifetime. In the third, the drawing repeats in a way that only becomes apparent if a marker appears twice from different directions. If my instruments only cover one short segment, all 3 maps may look identical. The question is not whether the maps differ in principle. It is whether the accessible evidence reaches the difference. That is the central discipline of this file. Cosmology often deals in possibilities that are mathematically distinct, but observationally hard to separate. An infinite flat universe and a finite flat universe with an enormous fundamental domain can be indistinguishable inside our horizon. A positively curved universe with a huge curvature radius can look flat. A topology scale far beyond the last scattering surface can leave no repeated microwave pattern for us to compare. The universe does not owe us a detectable answer. Inflation enters the case as both explanation and complication. The basic inflationary idea is that the very early universe underwent a brief phase of accelerated expansion. This could explain why the observable universe is so uniform, why its geometry appears so close to flat, and how tiny quantum fluctuations became the seeds of later structure. Inflation stretches curvature, dilutes relics, and makes a small patch appear enormous and smooth. Planck's measurements tested many inflationary predictions. They found a scalar spectral index less than 1, consistent with a red-tilted spectrum of primordial fluctuations. They found no strong evidence for running of that index. They constrained gravitational waves from inflation through the tensor to scalar ratio. Combined with BAO, Planck found spatial flatness to within about 0.4% at 95% confidence in the inflation constraints analysis. These findings support broad features of simple inflationary models, though they do not select one unique model from all possible versions. Inflation can make the observable universe look very flat, even if the total universe is not infinite. That sentence should be allowed to remain plain. A strong inflationary phase can expand a region so much that any original curvature becomes difficult to detect within the portion we can observe. The measured near flatness of our region is therefore not surprising in many inflationary models. But using inflation to claim that the whole universe must be infinite would go beyond the evidence. Inflation may imply that the universe is much larger than the observable region. Some models suggest eternal inflation or wider structures beyond our horizon. Those ideas belong to theoretical cosmology, not direct measurement of the total spatial extent. There is also a measurement limit that no improved telescope can simply erase. We observe one universe from one location, inside one finite horizon. Large-scale curvature measurements are affected by the fact that matter fluctuations exist within the observable volume. Even if the underlying universe had exactly zero average curvature on the largest possible scales, the region we observe can contain fluctuations that create a small, effective curvature-like uncertainty. This is sometimes described as a cosmic variance limit. It is a reminder that some uncertainty arises from the finite sample itself. We cannot observe another independent universe volume to average over. The instrument room is colder than my office. It sits near the forward sensor spine, where the ship keeps its oldest survey equipment alive by habit more than necessity. On one console, a screen displays a simple warning: finite baseline. The phrase belongs to interferometry, but it could be written across all of cosmology. Every measurement has a baseline, every map has a region, every inference has a model behind it. For the total universe, the baseline is the observable universe, and the model extends beyond it only as far as its assumptions are trusted. This does not make cosmology weak. It makes it honest. The strongest sciences are not the ones that pretend to know without limits. They are the ones that identify the boundary between measurement and extrapolation. In this file, that boundary is the subject. Humanity learned to measure the universe by accepting that distance and time are entangled. When we look far away, we look back. A galaxy seen at redshift 2 is not only far in space, it is seen at an earlier stage of cosmic history. A quasar at redshift 6 shows the universe when it was young. The CMB shows a still earlier epoch, but none of those observations gives a present-day photograph of the whole. They give slices through the past light cone. To reconstruct cosmic history, scientists fit models to those slices and ask which parameters make the observations consistent with one another. That is why distance measures matter. A luminosity distance is inferred from how bright an object appears compared with how luminous it is thought to be. An angular diameter distance comes from how large an object appears compared with its known physical size. A comoving distance factors out the expansion so that objects moving with the Hubble flow keep fixed coordinates. Look-back time describes how long the light has travelled. These are not competing answers to a simple question. They are different answers to different observational questions. In ordinary life, a distance is a length between two places now. In cosmology, now is local. There is no universal cosmic photograph that all observers can hold at once in the same practical sense. General relativity allows useful cosmic time in the standard homogeneous models, but observations arrive along light cones. The archive does not receive the universe as it is everywhere today. It receives signals from different ages, arranged by the paths they took to reach the observer. The universe's expansion also creates another limit, the event horizon in an accelerating universe. The particle horizon concerns what can have reached us since the beginning. The event horizon concerns what can ever reach us in the future if cosmic acceleration continues. Because dark energy appears to be driving accelerated expansion, there are galaxies whose light emitted today may never reach us, even given unlimited waiting time. The observable universe is not only a present archive, it is a changing archive. Some future evidence may arrive. Other evidence is forever excluded by the expansion history. This is not a reason for despair in the file, it is part of the structure of the case. The universe can be physically real beyond our horizon and still inaccessible to direct confirmation. The distinction feels severe because human intuition evolved in places where walking farther usually revealed more. Cosmology does not promise that. It gives us one past light cone and asks us to be exact. I passed through the hydroponics bay on my way back from the instrument room. Rows of plants grow under low amber lamps. Leaves turn toward an artificial day. Each tray is a local system with controlled light, water, and air. From one tray, a plant cannot see the whole bay. From the bay, I can see the pattern of trays. From outside the ship, the bay would be only a small green compartment inside a hull. Scale changes what can be inferred. A leaf can register light and gravity and moisture. It cannot map the vessel. An observer inside the universe has better instruments than a leaf, but not an outside vantage. The old cosmologists knew this. The better ones wrote with caution around totality. They used the cosmological principle because the observed universe looked homogeneous and isotropic on large scales, and because the principle made the equations tractable. They did not assume it because they had inspected all of space. The principle says, roughly, that we do not occupy a special location, and that the large-scale universe should be statistically similar elsewhere. It is supported by the CMB and by large-scale structure surveys. It remains an extrapolation beyond the observed region. This is a delicate point. Without the cosmological principle, cosmology loses much of its ability to infer global properties from local observations. With it, one can construct models that fit the data and extend beyond the horizon. The principle is not a guess pulled from nowhere. It is a symmetry assumption backed by evidence inside the observable universe. But any claim about the unobservable whole depends on extending that assumption. A calm scientific script should say this plainly. The question of infinity also depends on what kind of infinity one means. Infinite spatial extent is one idea. Infinite age is another. Infinite matter, infinite possible arrangements, infinite future, infinite inflationary domains. These belong to different questions. This episode should keep its eye on spatial extent and measurable cosmology. The universe appears to have a finite age since the hot, dense early phase. The observable region is finite. The total spatial universe may be infinite or finite. Those statements can coexist without contradiction. If space is infinite and matter is distributed with roughly uniform average density, then there may be infinitely many galaxies beyond the observable region. If space is finite, but much larger than what we can observe, the observable universe could still look exactly as it does. If space is finite with a compact topology small enough, repeated patterns might appear, and searches can constrain it. If the topology is finite but too large, the evidence may never reach around far enough to reveal it. The archive contains an older page from a topology review where the authors state in careful mathematical language that general relativity does not specify the topology of space. That sentence is one of the hinges of the whole case. Einstein's equations tell the metric how to behave locally in relation to matter and energy. They do not, by themselves, choose whether the global space is simply connected or multiply connected. A single local geometry can be compatible with more than one global topology. To make that less abstract, consider a flat video game plane where leaving one side of the screen brings an object back on the opposite side. Locally, movement obeys flat geometry. There is no edge to crash into. Globally, the space is finite in that direction. That is only a crude analogy, and it should not be mistaken for physical evidence. Its purpose is to loosen the grip of the assumption that flatness and endlessness are the same. The real mathematics in 3 dimensions is richer and less visual, but the principle survives. Could humans have detected such a topology through ghost images of galaxies? In principle, yes, if the topology scale was small enough and the images identifiable. In practice, galaxies evolve. A galaxy seen along 2 paths of different lengths would be seen at different times. Its shape, brightness, stellar populations, and environment could differ. Dust, lensing, selection effects, and incomplete catalogues complicate the search. The CMB is cleaner for this purpose because it comes from a single ancient surface and covers the whole sky. That is why matched circles became such an important test. The phrase circles in the sky has an almost poetic quality, but the method is statistical. One compares temperature fluctuations around pairs of circles on the CMB sky, allowing for relative phase and orientation. If a pair of circles represents the same physical ring on the last scattering surface, viewed along different paths, the pattern should match beyond chance. Foreground emission from our galaxy, instrumental noise, beam effects, and the integrated Sachs-Wolf effect can interfere, so the tests must be careful. Planck's data were the best full-sky microwave maps available for this kind of work, including polarization information that can be especially useful because much of it is generated near recombination. The result remains quiet, no detection. A lesser episode might treat that as an anticlimax. It is not. A negative result is a measurement with teeth when the search is well defined. It tells us that certain compact universes are not hiding inside the scale where they would have shown matched patterns. It narrows the map. The file becomes less vague. The absence has shape. Yet the compact collaboration and other researchers have argued that future topology searches still have room to improve. The search space for possible topologies is large. Even flat manifolds include more than the simplest torus. Some topologies produce anisotropic correlations that may be detectable without matched circles. Large-scale structure might eventually help in cases where the topology scale exceeds the last scattering diameter, though the problem becomes computationally and observationally difficult. The frontier is not a promise of discovery, it is a list of remaining tests. This is where I prefer the phrase constraint over answer. Cosmology constrains the possible. It makes the world of allowed models smaller. The best measurements do not always point to a single final sentence. They may say, this class is ruled out, this class is disfavored, this class remains consistent, this parameter is bounded, this inference depends on the model. There is elegance in that form of knowledge. It is harder to market than certainty, but it is closer to the truth. The quiet galley is empty when I enter. The ship keeps a kettle there for rituals no machine requires. I set it to warm and watch condensation gather briefly on the metal surface near the spout. A small cloud forms, changes, and disappears. Local structure, local physics, a tiny finite event inside a vessel moving through a universe whose total shape may be unknowable. The contrast is absurd and comforting. Science often works by making the vast submit to the small. A spectrum on a detector, a number in a table, a fluctuation in a microwave map, a ruler hidden in the clustering of galaxies. A question as large as infinity comes back, again and again, to instruments. Kobe measured the CMB spectrum and detected its anisotropies. WMAP mapped those anisotropies with better resolution. Planck improved the measurement of temperature and polarization, producing a high-precision view of the microwave sky. Galaxy surveys measured clustering across enormous volumes. Supernova surveys traced expansion through standardizable candles. None of these instruments was built to answer infinity in a single stroke. Together, they built the evidence framework in which the question could be asked scientifically. The scientific answer is therefore layered. The observable universe is finite. Its radius, in present-day co-moving terms, is about 46 billion light-years. That region contains the matter from which light has had time to reach us, though because of expansion and the opacity of the early plasma, our electromagnetic view has its own limit at the last scattering surface. Within that observable region, measurements show that the universe is very close to spatially flat. CMB data, especially Planck, combined with BAO measurements, strongly constrain curvature. If the universe has positive or negative curvature, the curvature radius is large compared with the scales directly accessible to us. A spatially flat universe may be infinite if it has the simplest topology. It may also be finite if it has a compact topology. General relativity does not settle topology by itself. Observational topology searches look for repeated patterns, especially in the CMB. Those searches have not found evidence for a compact topology on scales where the tested models would produce detectable signatures. Inflation explains why our observable patch could be so flat and uniform. It supports the idea that the total universe may be much larger than the observable region. It does not provide a direct measurement of infinity. Beyond the horizon, claims become model-dependent. The cosmological principle allows extrapolation. It is well supported inside the observable universe, but it is still an assumption when extended without limit. These points do not produce a dramatic yes or no. They produce a map of epistemology. Though that word belongs more to philosophy than narration, I would rather say this: humanity learned where the lamps reached. Back in the office, the observation dome has shifted to the ship's night cycle. The glass above me reflects a faint image of the desk, so that the folder appears superimposed on the stars. The archive projection still shows the sphere of observability, detailed within, fading without. I rotate it slowly. There is no preferred direction where the answer hides. The CMB surrounds us with old light. The galaxies recede. The BAO ruler repeats in statistics, not in a visible grid. The topology searches leave rings marked and unconfirmed. The case file asks whether the universe is infinite, but the evidence answers a slightly different question first. How much of the universe is available to measurement? That question has a firm answer. We can measure our past light cone. We can infer a large-scale model. We can test curvature and topology within the reach of observable signatures. We can say that the universe we see is consistent with spatial flatness and with the simplest infinite models. We can also say that finite models larger than the observable region or finite topologies without detectable signatures in our sky remain possible. One of the traps in this topic is the urge to turn uncertainty into atmosphere. The unknown beyond the horizon does not need to be made more dramatic. It is already severe. No signal from beyond the particle horizon has reached us. No telescope can gather photons that have not had time to arrive. No map can include regions outside the causal record unless a model is carrying the pen beyond the data. The model may be good. It may be the best available. It may be supported by every test inside the horizon, but it is still doing something different from observation. A scientist can use it. A narrator should name it. The same discipline applies to the word infinite. Infinity is not a very large number. It is not a distance one could cross given enough patience. It is a different kind of statement. No finite set of observations can prove spatial infinity in the way it can detect a finite repeated pattern. If space wraps around on a small enough scale, evidence might reveal the closure. If space never wraps around, every measurement still covers only a finite region. Observing more and more flatness over a larger and larger region can support infinite models, but it cannot finish infinity by direct inspection. That asymmetry is at the heart of the case. Finiteness can sometimes betray itself. Infinity can only remain consistent. There are mathematical theorems and observational strategies around this point, but the intuition is plain enough. If you live in a room whose walls are far beyond your lamp, and you find a repeating mark that could only come from the same wall seen twice through a mirror path, you have evidence of closure. If you do not find such a mark, the room might be open, or the walls might be farther away, or the marks might be hidden by fog, or the geometry might not match the simple plan you tested. The absence of closure is informative. It is not the same as proving endlessness. In cosmology, the fog is not only dust or noise. It is the finite age of the universe, the last scattering surface, cosmic variance, foregrounds, model degeneracies, and the fact that we observe from one location. The instruments are extraordinary. The problem is still larger than the instruments. The historical record shows that every time humans enlarged the universe, they also enlarged the unknown. The Earth moved from center to planet. The Sun became one star among many. The Milky Way became one galaxy among many. The observable universe became a finite region within whatever the total universe may be. The pattern is tempting, but it should not be abused. History does not prove the next enlargement. It only warns against confusing the edge of the map with the edge of reality. The case, therefore, does not end with an answer written in heavy ink. It ends with a set of findings. The universe is not known to have an edge. The observable universe has a horizon. The measured spatial curvature is very close to zero. The simplest model, consistent with the data, is spatially flat and infinite. Flatness alone does not prove infinity. Topology searches have found no evidence that space repeats on the tested scales. Inflation can explain why the observable region is so flat, but it does not turn the unobservable whole into a measurement. Beyond the horizon, cosmology works by disciplined extrapolation. I close the folder halfway and leave the projection running. The sphere of the observable universe hovers over the desk, its inner structure still visible. Clusters, filaments, microwave texture, the faint statistical memory of ancient sound. Outside the sphere, the display fades. It does not go black. It does not draw a border. It simply declines to invent data. That restraint is one of the most human things in the surviving archive. The old scientists wanted answers as badly as anyone. They built machines on mountaintops and in orbit. They chilled detectors near absolute zero. They mapped galaxies by the millions. They turned the whole sky into a statistical instrument. And when the measurements reached their limit, the best of them did not fill the silence with certainty. They wrote constraints. They wrote confidence intervals. They wrote consistent with. They wrote no detection. They wrote cannot yet determine. Those phrases may look modest beside the word infinite, but they are the bones of the case. Without them, the answer would be easier and less true. The ship continues through the dark between stars. From the observation dome, the universe looks open in every direction. That appearance is not evidence of infinity. It is evidence of scale, distance, and the poverty of any horizon-bound eye. Somewhere beyond the oldest light we receive, space may continue without end, or it may close so gently across such a vast distance that no signal in our sky can reveal the turn. The difference matters. The inability to decide it completely also matters. For now, the recovered knowledge is this: the universe we can measure is immense, expanding, ancient, and close to flat. The universe beyond measurement remains beyond the file, and the most careful answer to the question, is the universe infinite, is not yes and not no. It is, we do not know, but we know exactly why we do not know. And that is not ignorance in the ordinary sense. It is the shape of the evidence itself. I leave the case open beneath the lamp for a little longer. The title on the folder has stopped looking like a demand. It looks more like a coordinate, a point in the archive where measurement meets its horizon, and where the old human habit of asking still outlives the reach of the instruments that tried to answer. The file has another compartment beneath the first set of notes. It opens with a small resistance, as if the folder itself is reluctant to give up the older material. Inside are records from a time when the word universe meant something smaller than it would later become. The first drawings are not wrong in the careless sense. They are human attempts to give shape to a sky that offered almost no depth cues. A sphere of stars, a wandering set of planets, a moon close enough to mark the months, a sun bright enough to rule the day. The early maps were built from appearances, and appearances were all the observers had. One of the gentle dangers in reconstructing science after the fact is the temptation to look backward with too much certainty. It is easy to stand inside a later model and treat earlier models as foolish. The better habit is to ask what evidence was available. If all the stars seem fixed on a sphere, and the planets move against them, and there is no measured stellar parallax, a finite layered cosmos has a certain practical coherence. It is not the final answer, but it is not a random answer. It is a model shaped by the reach of the instruments. The case of infinity has always been tied to instruments. The unaided eye made one kind of universe, The telescope made another. Spectroscopy made another. Photographic plates and radio receivers and orbital observatories made another. The universe grew each time the evidence gained a new kind of reach. The old file marks one transition with a sketch of a small glass lens. After the telescope, the Moon acquired mountains, Jupiter acquired moons. The Milky Way became a dense field of unresolved stars instead of a pale celestial stain. The planets stopped looking like wandering lights and became worlds. The sky's apparent dome began to lose its authority. Still, even then, the question of the universe's total size remained mostly outside measurement. Seeing farther did not yet mean measuring the whole. The next records belong to stellar parallax and the slow discovery of distance. Parallax is ordinary in principle. Hold a finger up and view it with one eye, then the other. It shifts against the background. A nearby star should shift against more distant stars as Earth moves around the Sun. For centuries, no such shift could be measured, and that absence was used to argue the Earth did not move. Later instruments found the shift at last. The stars were simply very far away. The lack of parallax had not meant the Earth was fixed. It had meant the baseline was too small, and the stars were too distant for the old instruments. That is an important pattern for this episode. A non-detection may mean a thing is absent. It may also mean that the scale of the effect is beyond the apparatus. Cosmology learned this lesson repeatedly. No parallax became evidence of great distance. No stellar edge became evidence that the Milky Way was not easily bounded by vision. No matched circles in the microwave background became evidence against some compact topologies, not against every possible finite universe. The interpretation depends on what the test should have detected. I take the parallax plate down to the instrument room and set it under a narrow scanner. The plate is old enough that its emulsion has cracked into a network of fine lines. The machine compensates, reconstructing the star positions from multiple exposures. A nearby star has shifted by a fraction so small it would vanish under a careless eye. Yet that fraction opened depth in the sky. The same principle, carried to larger and stranger scales, runs through the whole history of cosmology. The universe is not measured by staring harder. It is measured by finding effects small enough to preserve the truth. By the 19th century, the Milky Way had become a problem of structure. Was it the whole universe, an island of stars surrounded by emptiness, or one system among others? Spiral nebulae lay in the records as ambiguous evidence. Some looked like clouds. Some looked like star systems. Their distances were disputed because the available methods were not yet strong enough. The question was not merely whether a given nebula was large or small, it was whether the visible universe ended at the Milky Way or continued into a larger population of galaxies. That dispute finally changed when variable stars became distance markers. Cepheid variables have a relationship between their pulsation period and intrinsic luminosity. Measure the period, infer the true brightness, compare it with the apparent brightness, and the distance follows. When Edwin Hubble identified Cepheids in the Andromeda Nebula, Andromeda moved outside the Milky Way. It became a galaxy in its own right. The universe widened again. The file pairs that record with another galaxy redshifts. Vesto Slipher measured the spectra of spiral nebulae and found that many were shifted toward the red. Later, Hubble and others connected distance with recession, producing the relationship now known as Hubble's law. The farther away a galaxy was, the faster it appeared to be receding. The universe was expanding. A static arena gave way to a changing metric. Expansion altered the infinity question. In a static universe, distance was a spatial problem only. In an expanding universe, distance became a problem of space-time history. A galaxy's light carries information from the time it was emitted. The redshift tells us how the scale factor changed while the light was travelling. A distant object is not simply far away, it is seen in the past. To ask how large the universe is now, one must pass through a model connecting light, time, expansion, and geometry. In the galley, the kettle has cooled, and the metal surface no longer carries condensation. I pour water into a dark cup and watch the surface settle. The ship's gravity is steady enough that the reflection becomes a small circular mirror. For a moment, it holds the ceiling light, the shelf above me, the edge of my hand. It is a complete little image of a limited angle. Nothing in the reflection says the galley ends at the cup's rim. The rim belongs to the observing system, not to the room. Our past light cone is far more profound than a reflection in water, but it shares that warning. A field of view is not a universe. The next set of notes in the file concerns horizons. The word horizon is dangerous because it sounds like a place. On Earth, a horizon is where the surface curves out of sight, and a traveller can move towards it. In cosmology, different horizons mean different limits in space-time. The particle horizon is the maximum distance from which light could have reached us since the beginning of the hot expanding phase. The event horizon, if the acceleration continues, is a limit on what can ever reach us in the future. The Hubble sphere is the distance where recession speed equals light speed in the usual expansion description. It is not a true horizon. The difference matters enough to slow down. Suppose a distant galaxy is beyond the Hubble sphere at the time it emits a photon toward us. In proper distance coordinates, the photon may initially be carried away from us because the space between us and the photon is expanding so fast. Later, as the Hubble sphere changes, the photon can move into a region where it approaches us. It can eventually arrive. This is why we can see galaxies that were receding faster than light at the time the light was emitted, and why statements about faster than light recession must be handled within general relativity. The Hubble sphere is a useful surface, but it is not the edge of observability. The particle horizon is closer to what people often mean when they ask how far we can see, though even that phrase needs care. We can receive light from the hot plasma only back to the surface of last scattering. Before that, the universe was opaque to ordinary light. We infer earlier conditions from the CMB, nucleosynthesis, particle physics, and the pattern of perturbations, not by seeing photons from the first instant. The observable universe is therefore built from several limits. There is the age of the universe. There is the finite speed of light. There is the expansion history. There is the opacity of the early plasma. There is the practical sensitivity of instruments. Each limit has a different role. Confusing them produces easy but wrong sentences. I bring up the horizon diagram on the observation dome. The ship dims the office lights until the glass overhead becomes a black field crossed by mathematical lines. Our world line runs up the centre. The past light cone widens backward, then meets the early universe. The Hubble sphere curves through the diagram. The particle horizon and event horizon take their own paths. It is not a picture of space alone. It is a picture of space-time. and that is why it resists the habits of ordinary seeing. A common question follows naturally. If the observable universe has a radius of about 46 billion light-years, does that make the universe at least 92 billion light-years across? The answer is that the observable region measured across is about 93 billion light-years in present-day co-moving diameter. But that is only our observable region. The total universe, if larger, does not have a measured diameter from our data alone. It could be only somewhat larger than the observable region, though topology searches constrain some versions of that possibility. It could be vastly larger. It could be infinite. The number 46 billion light-years also needs context. It is a present-day co-moving distance to matter whose light was emitted long ago. The light did not travel for 46 billion years. It travelled for nearly the age of the universe. During that time, the scale of space changed. If we ask where that matter is now in the coordinates of the standard model, we get the larger number. This does not violate light speed. It reflects expansion during the light's travel. Hogg's distance notes in the archive treat this with the plainness of a technical manual. Cosmology has many distance measures because the universe is expanding and because observations reach us along null paths, the paths of light. Luminosity distance, angular diameter distance, co-moving distance, look-back time, and proper distance all answer different questions. If a script collapses them into one ordinary distance, it will feel simpler and become less accurate. So the episode should let the listener sit with the complexity without drowning them in notation. A galaxy can be described by the time its light has travelled, the redshift of that light, its co-moving distance now, its angular diameter distance when we infer its size, and its luminosity distance when we infer its brightness. These are not evasions. They are the cost of measuring a universe where space and time are joined dynamically. The historical file then turns to the microwave background, and here the paper changes texture. The older pages are full of optical plates and galaxy spectra. The CMB pages are machine clean, covered in maps, masks, multipoles, foreground models, and likelihood curves. The discovery of the cosmic microwave background in 1965 gave cosmology a relic rather than a distant object. The radiation came from everywhere in the sky, nearly the same in every direction, cooled by the expansion of the universe. It fit the hot Big Bang model with a force that older arguments had lacked. Later missions turned that radiation into a precision instrument. COPE showed that its spectrum was an almost perfect blackbody and found the first anisotropies. WMAP mapped the anisotropies in detail. Planck measured them with still greater precision across temperature and polarization. These variations are tiny, on the order of tens of microkelvin, but they contain a record of early density fluctuations, acoustic oscillations, and the composition of the universe. In the holographic evidence bay, I let the CMB sphere fill the room again, larger this time. The surface looks textured, but the texture is exaggerated for human eyes. Without amplification, the temperature differences would be almost invisible against the uniform glow. The old universe was smooth to about 1 part in 100,000, and yet that tiny unevenness was enough. Gravity amplified it over billions of years into galaxies, clusters, and the large-scale structure that later surveys mapped. The CMB is central to the infinity question because it gives us a standard ruler at an enormous distance. The early photon baryon plasma supported sound waves, gravity compressed regions, radiation pressure pushed back. The result was a pattern of oscillations with a characteristic sound horizon at recombination. That scale imprinted itself in the temperature fluctuations. When we measure its angular size on the sky, we are measuring how geometry and expansion carried that ruler to us. If space had strong positive curvature, the paths of light would make the ruler appear larger than in flat space. If space had strong negative curvature, it would appear smaller. The observed angular scale, combined with a model of the sound horizon and other cosmological parameters, gives a curvature constraint. The first acoustic peak sits near the position expected for a flat universe. Planck made this statement precise. But the CMB alone has degeneracies. One can adjust curvature and dark energy parameters in ways that preserve the angular acoustic scale. Planck's own lensing measurements help, and external data help more. BAO is especially valuable because it supplies lower redshift distance information from the distribution of galaxies. This is why Planck plus BAO becomes such a strong combination in curvature constraints. In the instrument room, the ship's archive displays two curves. One comes from the CMB alone, elongated along a degeneracy direction. The other tightens when BAO is added. The final allowed region shrinks near zero curvature. The display is less dramatic than a picture of a galaxy, but it is the kind of evidence cosmology often depends on, a narrowing of parameter space. The beauty lies in the constraint. The listener does not need every parameter in the lambda cold dark matter model, but the script should name the model's role. Lambda CDM includes ordinary matter, cold dark matter, radiation, neutrinos, and dark energy represented by a cosmological constant. It assumes large-scale homogeneity and isotropy, and a primordial spectrum of mostly adiabatic, nearly Gaussian scalar perturbations. Within that model, the Planck data are fitted with high precision. When curvature is allowed as an extension, the data combined with BAO remain consistent with flatness. The word consistent is doing serious work. It does not mean confirmed in an absolute sense. It means the measured values do not require curvature different from zero within the uncertainties and assumptions. A closed universe with an enormous curvature radius can still mimic flatness over our observable patch. An infinite flat universe fits well. A finite flat topology can also fit locally if its topology scale is too large or otherwise undetected. The curvature measurement removes many possibilities. It does not remove all of them. There is a familiar teaching image of ants walking on a balloon. It can help explain two-dimensional positive curvature, but it can also mislead. People begin asking what the balloon expands into, or where the center is. A two-dimensional surface does not need a center within the surface. The balloon has a center because it is embedded in our three-dimensional space. But the mathematics of curvature does not require an outside space in the same way. Cosmological expansion is not galaxies flying away from a central explosion into pre-existing emptiness. It is an increase in scale between co-moving points. The archive marks this warning in red. Do not put the Big Bang at a place. In the standard model, the hot, dense early state happened everywhere in the observable universe. Every distant galaxy, if traced back through the expansion, was part of the same hot, dense state. The CMB comes from all directions because every direction reaches back to that early transparent surface. The expansion has no center in space. Every co-moving observer sees other distant galaxies receding on average in the same large-scale way. This has a direct bearing on infinity. If the universe is infinite now, it may have been infinite at earlier times too, with the scale factor smaller, but the spatial extent still without bound. The Big Bang was not necessarily the creation of space from a point in space. In the standard equations, the scale factor approaches zero in the past, and densities and temperatures become extreme. How that relates to an initial singularity or a quantum gravity phase remains an open question. The script should not present the Big Bang as a tiny object exploding into a void. That image is common and wrong enough to damage the episode. I step into the maintenance passage that runs near the engine spine. Here, the ship is louder. Not loud in a dramatic way, but alive with low vibration, coolant movement, and the faint tick of expansion joints adjusting to temperature. The passage is narrow, and its walls are close enough that a hand can touch both sides. Yet the ship's navigation system knows this passage as part of a larger vessel, and the vessel as a point on a route no wall inside it can reveal. Local experience is not global knowledge. The same is true of curvature. A local patch of a curved space can look flat. The better the measurements and the larger the patch, the more strongly curvature can be constrained. But if the curvature radius is far beyond the observable universe, the measured patch will remain nearly Euclidean. There is a point where improved instruments run into the sample size of the universe available to us. Cosmic variance is one form of that limit. In the CMB, cosmic variance appears because we have only one sky to observe. For the largest angular scales, there are only a few independent modes. No instrument can observe another independent realization of the universe's largest scale fluctuations from our position. Lower noise helps at smaller scales, better foreground cleaning helps, polarization helps, but the number of larger scale modes is fundamentally limited. The universe gave us one microwave sky. For curvature, local fluctuations also matter. The observable universe is not perfectly smooth. It contains density perturbations. Those perturbations can affect the curvature inferred within our finite region. If the underlying curvature is below a certain level, distinguishing exact flatness from extremely small curvature becomes statistically and physically difficult. This does not mean curvature is meaningless. It means there is a floor below which the question becomes less knowable from inside our horizon. The paper by Vardanyan, Trotter and Silk sits in the file near this issue. Its title asks how flat one can get. It treats curvature through Bayesian model comparison and discusses how the geometry may become unknowable below a threshold around 1 part in 10,000 for the curvature parameter, depending on the context and the problem of model confusion. The exact number belongs in the research notes, not necessarily in the narration, but the lesson belongs in the script. There are limits that come from theory, limits that come from instruments, and limits that come from observing one finite region of a lumpy universe. A careful episode can make this almost physical. If a surveyor is confined to a small valley on an enormous planet, the land may appear flat. Better instruments can detect curvature eventually, but only if the surveyed region is large enough compared with the planet. If the planet is too large, local hills and valleys may dominate the measurement. Cosmology faces an analogous problem with the observable volume and primordial perturbations. The analogy is imperfect, but the caution is sound. The next part of the file returns to topology and it does so with a small historical note that feels almost out of place. Schwarzschild considered multiply-connected cosmic spaces as early as 1900, before general relativity was complete. The possibility that the universe might create multiple images through its topology is not a modern fantasy added to cosmology for atmosphere. It has a long mathematical history. General relativity made the question deeper by distinguishing local geometry from global structure. Luminet's topology review in the archive has a useful phrase: "A finite universe need not have an edge." That one idea deserves time in the script because it corrects one of the strongest everyday intuitions. Finite things in ordinary life have boundaries. A table ends. A room has walls. A planet has a surface. But a closed surface, such as the surface of a sphere, is finite in area and has no edge within the surface. A three-dimensional universe can be finite in volume without any boundary one could reach. Positive curvature gives one route to finite volume. Non-trivial topology gives another. A flat torus is finite without local curvature. Hyperbolic spaces can also be finite under compact topologies. The classification of possible three-dimensional spaces is richer than the simple schoolbook set of open, flat, closed. For an episode, the goal is not to catalogue all manifolds. It is to teach the separation. Curvature is about geometry. Topology is about connectedness. The central archive chamber can carry this part. I see Madeline moving around the cartography table while the table projects a flat square whose opposite edges are identified, then a cube, then a more abstract three-dimensional cell. The narration should be careful not to imply physical walls at the edges of the cell. The cell is a representation, a fundamental domain. In the actual space, a traveller would not hit an edge. Paths are identified by the topology. In a finite multiply-connected universe, light can take multiple paths from the same source to the observer. If the paths are short enough, one might see repeated images. But those images would not necessarily look identical. A galaxy seen along a longer path is seen at an earlier time. A galaxy can merge, form stars, dim, brighten, change shape. The CMB avoids some of that time evolution confusion because it is a single ancient surface. That is why the matched circles method has such clean conceptual force. The circles come from geometry. In the covering space representation, copies of the observer have their own last scattering spheres. If our last scattering sphere intersects one of its copies, the intersection is a circle. The same physical points on the surface of last scattering would appear in two directions, producing matched temperature patterns along the paired circles. The details depend on the topology, orientation, and whether polarization is included, but the basic signature is visual and testable. Planck's 2015 topology paper is therefore one of the core sources for this episode. It used temperature and polarization data to search for matched circular patterns and to perform likelihood calculations for specific topologies. It found no detection for compact topology with a scale below the diameter of the last scattering surface in the tested cases. The cubic torus and slab limits are concrete enough to mention, though the script should frame them as examples of constrained models rather than the final word on topology. The compact collaboration's later work gives the counterweight. It argues that previous searches have not exhausted the possible topology parameter space, even in flat manifolds. Matched circles are powerful when the topology scale is small enough, but anisotropic correlations can persist in cases without visible matched circles. Some searches are computationally formidable because one must scan over many possible topologies, sizes, shapes, orientations, and observer positions. This is a legitimate frontier, not a loophole invented for drama. That distinction matters. We should not write as though scientists are clinging to topology despite evidence. We should write that the evidence has ruled out certain detectable versions and left others open. The file is narrower than before, not closed. I return to the observation dome late in the ship's cycle. The star field has rotated by a small amount relative to the frame marks on the glass. Of course, the stars have not rotated around the ship in any simple, absolute way. The ship has adjusted attitude, the reference frame has changed. The lesson is small but useful. What one sees depends on where one stands and how one measures. Cosmology is built from transforming observations into quantities that can be compared across a model. Redshift becomes scale factor, angular size becomes distance, temperature fluctuations become power spectra, galaxy positions become correlation functions, patterns become parameters. The raw sky is not enough. It has to be reduced, calibrated, cleaned, masked, modelled and tested. None of that makes it less real. It makes it scientific. Foregrounds are part of that realism. The CMB is not observed on a pristine sky. Our galaxy emits microwaves, dust, synchrotron radiation, free emission, point sources, and instrumental effects complicate the maps. Planck used multiple frequency channels and component separation methods to estimate the CMB signal. Masks remove contaminated regions. Simulations test whether apparent features could arise from noise, systematics, or statistical fluctuation. A claim about topology or isotropy has to survive that machinery. This is useful for the eventual script because it keeps the episode grounded. The universe is not revealed to humanity as a clean diagram. It is extracted from contaminated data. That fact can be cinematic in a restrained way. Old instruments, foreground dust, damaged maps, careful subtraction. Madeline, as an archival intelligence, fits this naturally. She is not staring at a perfect cosmos. She is reconstructing it through surviving records, each with uncertainties attached. The isotropy paper adds another layer. Planck found the temperature anisotropies consistent with the Gaussian predictions of lambda CDM, while confirming several large angle anomalies. Polarization analysis was more limited by residual systematics and noise, especially on large scales, though it provided important tests. This is a careful result. It does not support turning anomalies into a grand claim. It supports mentioning them as unresolved features that motivated further tests, including topology and anisotropy searches. The script should resist the false pleasure of saying the anomalies might be clues to a finite universe unless it immediately adds that no such interpretation has been established. A better phrasing would be that anomalies keep the largest scales scientifically interesting, but current evidence does not identify them as topology. That keeps the listener inside the evidence. The middle of the episode can therefore move through three nested maps. The first map is the observable universe. What can send signals to us? The second map is the geometric universe. What curvature measurements say about space on large scales? The third map is the topological universe, whether space's global connectedness might be finite or repeating. Each map has stronger and weaker evidence. Each map reaches a different kind of limit. I know the earlier instruction warns against overusing neat structures, and the script should not present this as a numbered lesson. but internally, this progression will help the long-form narration breathe. The listener can feel the investigation move from horizons to geometry to topology, then to inflation and uncertainty. That path mirrors the scientific hierarchy: what we see, how we measure its geometry, what its global connectedness might be, and what early universe theory implies. Inflation should enter after topology, not before, because inflation can otherwise flatten the narrative too early. If the episode begins by saying inflation makes the universe huge and flat, the listener may think the question is solved. Better to first establish the observable limit, then curvature evidence, then the topology trap. After that, inflation becomes an explanation for why the observable universe looks the way it does, and a warning that a flat observable patch may be only a tiny portion of a larger whole. The Planck inflation paper gives several useful anchors. Planck temperature, polarization, and lensing data constrain the scalar spectral index. They find no evidence for a scale dependence of that index. They constrain the tensor to scalar ratio when combined with BICEP and Keck data. They support key predictions of standard single-field slow-roll inflationary models, while leaving model selection open. For this episode, the most relevant point is that Planck plus BAO finds consistency with spatial flatness at high precision. The script can mention that inflation predicts a universe very close to flat in many models, but it should not pretend inflation is a completed theory of the total cosmos. There is also the issue of eternal inflation and multiverse language. It would be easy to drift there. The prompt asks for hard science and no speculative filler, so the episode should keep eternal inflation at the edge or omit it entirely. A brief sentence could acknowledge that some inflationary models extend far beyond the observable region, but the script should return immediately to what measurements constrain. This is not the multiverse episode. It is the measurement boundary episode. The end of section 2 should leave the file in motion rather than close it. We have expanded the historical and measurement frame. We have prepared the ground for the deeper topology and inflation sections. We have also established that the final answer will be constrained, not absolute. I place the older plates back into the drawer and let the archive vault seal itself. The file has changed shape in my hands. It no longer feels like a single question waiting for a yes or a no. It feels like a stack of different questions that humans learned to separate only after centuries of mistakes. How far can light have travelled? How does expansion change distance? Is space curved? Is it connected simply or in some hidden way? Does a near-flat observable region imply endless space, or only a curvature too small for our horizon to reveal? The vessel hums around me, a finite structure moving through a universe whose total structure remains unverified. Every corridor has a length, every room has a wall, every archive drawer has a back. It is almost impossible for a mind built from human memory not to expect the same of space. Yet cosmology spent generations teaching that ordinary expectation to loosen its grip. A finite universe need not have a wall. An infinite universe need not be directly provable. A horizon need not be an edge. A flat patch need not be the whole plane. The next evidence packet waits in the central chamber. It contains the most visual part of the case, the search for repeated light, matched microwave circles, and the possibility that the universe could be smaller than it appears without ever showing us a boundary. I leave the office lamp on behind me and carry the open file down the corridor. toward the place where the ship keeps its maps of spaces that may never be fully mapped. The central archive chamber is the oldest room still functioning without complaint. It lies deep in the vessel, below the observation dome and forward of the engine spine, where the hull's vibration becomes a low physical presence rather than a sound. The chamber was built for maps too large for ordinary displays. Its floor can hold a planetary survey. Its walls can hold a spectral archive. Its ceiling can project a sky around the observer until every direction becomes evidence. I carry the open file to the circular table at the centre and set the pages down beneath the scanning glass. The table reads the labels one by one: curvature, horizon, topology, inflation, cosmic variance. The words rise as faint blue text and arrange themselves around the room, each waiting for its place in the case. The topology packet opens first. There is a reason topology feels more unsettling than curvature. Curvature can be drawn, at least in reduced form. A sphere curves, a saddle curves. A flat plane does not. Topology asks a less visible question. If you travel straight long enough, could you come back to where you began? Could the same region of the early universe appear in two different parts of the sky? Could space be finite without any wall, edge, or outside surface? Those questions do not fit neatly into ordinary sight. They belong to paths. The archive begins with the simplest teaching model, a flat square whose opposite edges are identified. When a marker crosses the right edge, it reappears from the left. When it crosses the top, it returns from below. The marker has not bounced. It has not passed through a physical frame. The frame is only a drawing of the fundamental domain. The actual two-dimensional space, if such a creature lived within it, would have no detectable edge at the crossing. It would feel locally flat everywhere. The table then lifts the square into a cube. Opposite faces are paired. A beam of light leaves one face and enters from the opposite face. A three-dimensional torus is not a donut in ordinary three-dimensional space, despite the name people often use for its lower dimensional analogy. It is a way of identifying positions in a flat three-dimensional geometry. Locally, all the rules of Euclidean geometry can hold. Globally, space can still be finite. This is the part that needs patience. The universe does not have to be embedded in a higher space for its topology to be meaningful. We draw embeddings because human vision likes pictures. The mathematics does not require the picture. The surface of Earth is finite and unbounded for a traveller confined to the surface, even though we can picture it from outside in 3 dimensions. A three-dimensional space can be finite and unbounded without needing a literal outside for us to look from. The file contains older examples of multiply connected spaces, spherical spaces, Euclidean compact spaces, hyperbolic compact spaces. Some preserve orientation, some do not. Some are finite in all 3 spatial dimensions. Some are finite in 1 or 2 directions, and infinite in others. The detailed classification is too large for a single narration, and it would pull the episode away from its main evidence. The useful point is that topology gives cosmology more possibilities than the simple phrase open, flat, or closed suggests. In the simplest classroom language, positive curvature often gets associated with finite space, flat, and negative curvature with infinite space. That is only true under the simplest topology assumptions. A flat space can be finite. A negatively curved space can be finite. The local curvature and the global connectedness are separate pieces of the case. The chamber dims. A sphere appears overhead, the surface of last scattering, reconstructed from microwave data. Then another sphere appears, slightly offset, a copy generated in the covering space of a hypothetical topology. Where the two spheres intersect, a circle forms. The circle glows, then another matching circle appears on the opposite side of the projected sky. This is the matched circles idea. If the topology of space makes our view wrap around, then the same physical region of the last scattering surface may be visible in more than one direction. Since two spheres intersect along a circle, the repeated region should appear as pairs of circles in the cosmic microwave background. The temperature pattern along one circle should match the pattern along another, with the exact relationship depending on the topology and orientation. It is one of the rare moments in this topic when a difficult global question becomes almost tactile. The universe may be too large to measure by sending probes. It may be impossible to see beyond the last scattering surface with ordinary light. Yet a finite topology small enough to fit inside our observable region could leave fingerprints on the oldest light we have. The test does not require leaving the universe. It requires comparing the sky with itself. The method is elegant, and the data are difficult. The microwave sky is not a clean laboratory image. The Milky Way crosses it with foreground emission. Dust shines. Electrons scatter. Instruments have beams, calibration errors, noise, and scanning patterns. Analysts mask contaminated regions, separate frequency components, simulate skies, and ask how often chance alignments might imitate a real signal. A matched circle must survive all of that. There is also the matter of polarization. Temperature fluctuations in the CMB are powerful, but some temperature features are affected by processes after recombination along the line of sight. Polarization is generated strongly at last scattering and can provide a cleaner geometric test in some respects, though it is harder to measure with high signal-to-noise across the full sky. Planck's topology work used temperature and polarization data to improve the search. In the projection, the circle pairs rotate slowly. Most alignments fail. Patterns slide past one another without correlation. The archive overlays statistical thresholds. Chance is patient. Given enough possible circles, some will look tempting for a moment. The analysis has to account for that search space. It must ask not only whether a pair looks similar, but whether the similarity remains meaningful after all the possible circle pairs have been considered. This is one of the places where the old records feel most like a cold case. The evidence is everywhere, spread across the full sky, but the thing being searched for is a repetition that may not exist, or may exist in a form the search is not tuned to find. Every false match has to be dismissed without emotion. Every surviving candidate has to be tested against foregrounds, masks, and simulations. The case is not solved by wanting the pattern to be there. Planck found no convincing matched circles. Its likelihood searches for specific topologies also found no evidence for the compact models examined. For a cubic 3 torus, it constrained the size of the fundamental domain so that a small wraparound universe of that simple type is ruled out below a scale near the last scattering distance. For a slab topology, where only one direction is compact, the limits differ. The details depend on the topology, but the broad finding is clear enough for the narration. Planck did not reveal a small, repeating universe. I let the projection remove each rejected circle pair until only the microwave sky remains. The absence is almost as important as a detection would have been. It means that if the universe has a compact topology, it is not showing up in the tested ways at the tested scales. That statement removes some finite universes from the allowed file. It is real progress. It is also limited progress. The next page in the archive is a warning against a common overreach. No matched circles does not mean infinite space. A topology scale larger than the diameter of the last scattering surface would not necessarily create intersecting circles. A more complicated topology might create correlations that are not easily captured by the simplest searches. The observer's position can matter in some spaces. Orientations, twists, and shape parameters enlarge the search. Even among flat Euclidean possibilities, the space of models is broader than the simplest cube with opposite faces identified. The compact collaboration's later work presses this point. Past searches have tested important cases, but they have not exhausted all plausible topology signatures. Topology can create anisotropic correlations in the CMB even when matched circles are absent. Future searches may examine wider parameter spaces, use improved polarization, or combine microwave data with large-scale structure. That future is not a promise. It is an unfinished method. The distinction is precise. If a small cubic torus had shaped the observable universe, Planck should have had a chance to see its repeated microwave circles. It did not. If space is finite on a much larger scale, or finite through a topology whose signatures do not produce detectable matched circles in our sky, Planck's non-detection cannot decide it. A negative result is strongest against the signal it was built to find. The table shifts from circles to correlations. Instead of visible rings, the projection shows a matrix of CMB modes, multipoles, and off-diagonal structure. In a statistically isotropic universe, the correlations have a simple form. Topology can break that simplicity. The universe might not repeat in a way that draws bright rings on the sky, but it could still leave a pattern in the statistical relationship between modes. Searching those patterns is harder. It requires large calculations, clean data, and careful treatment of chance. The old case remains open partly because the evidence space is so wide. I move away from the table and walk along the circular gallery that surrounds the chamber. The gallery is finite. It returns me to the place where I began. It has no endpoint, only repetition. After one circuit, I pass the same wall panel again, then the same service hatch. If I did not remember the path, if the lighting were uniform and the markings removed, I might mistake repetition for endlessness. A finite loop can feel infinite from the inside if the clues are hidden. Space, if finite in this manner, would not be a corridor with visible, repeating wall panels. The analogy is too simple, but it carries the one lesson needed here. The absence of an edge tells us less than intuition wants it to tell us. Edges are not required for finiteness. The next evidence packet shifts from topology to inflation. The ship's lights soften as the archive reconstructs a timeline on the chamber wall. At one end is the hot, dense early universe. Then a small shaded region, almost too narrow to see, expands until it fills the wall. Inflation, if it occurred in the broad way described by the best supported models, was brief and enormous in consequence. A tiny region could be stretched until it became far larger than the observable universe. Curvature could be diluted. Initial irregularities could be smoothed. Quantum fluctuations could be enlarged into density perturbations, later recorded in the CMB. Inflation did not enter cosmology as a decoration. It was proposed to solve real problems in the hot Big Bang model. Why the observable universe is so uniform across regions that would not have been in ordinary causal contact without an earlier phase. Why the spatial curvature is so close to zero. Why certain unwanted relics are not observed, and how the seeds of structure could arise. Over time, inflation became a family of models rather than a single mechanism. Some have survived observational tests better than others. Some have been ruled out or disfavored. The general idea remains influential because it explains several features with one early dynamical phase. Planck's measurements did not prove every detail of inflation. They tested predictions. The primordial scalar fluctuations are close to Gaussian and adiabatic. The scalar spectral index is less than 1, meaning the spectrum is slightly red-tilted. There is no strong evidence for running of that index in the Planck analysis. Tensor modes, which would indicate primordial gravitational waves from inflation, are constrained but not detected at the levels once hoped for. Combined with BICEP and Keck data, Planck placed strong upper limits on the tensor to scalar ratio. For this episode, inflation's most important role is the flatness question. Inflation naturally drives the observable region toward flatness. If space expands by an enormous factor, any pre-existing curvature becomes harder to detect within the stretched patch. A small section of a curved surface can look flat when magnified enough. In a similar way, inflation can make our observable universe look extremely flat, even if the global universe has curvature or topology beyond our reach. That is why the measured near flatness of space supports inflationary expectations, but it does not settle infinity. A flat observable patch is compatible with an infinite flat universe. It is also compatible with a universe so large or so gently curved that our patch cannot reveal the whole. Inflation can enlarge the unknown along with the known. The archive displays a simple line from the inflation records. Planck combined with BAO finds spatial flatness to high precision. Then it places another line beside it. Precision on curvature is not proof of global topology. The two statements must remain side by side. If separated, they become misleading. This is where popular explanations often hurry. They say the universe is flat, therefore infinite. Or they say inflation makes the universe huge, therefore it is effectively infinite. The first claim confuses geometry with topology. The second replaces measurement with scale. A universe can be effectively infinite for all practical observation and still finite in total. A model can suggest enormous extent and still fall short of direct evidence for infinity. The word effectively is useful in engineering and dangerous in ontology. If the total universe is so large that no signal can cross it into our horizon, then for observation it may behave as though it were infinite. But the question in the file is not only what affects us, it is what can be known. A finite universe beyond all possible detection and an infinite universe can be observationally indistinguishable from within one horizon. In that case, science may prefer the simpler model, or the model best supported by the broader theory, while still acknowledging that the distinction remains unmeasured. I take the inflation page to the observation airlock. The airlock is sealed, cold, and rarely used except for exterior inspections. Beyond its small window, the ship's hull slopes away into dark. There is no sense of motion unless the navigation overlay is active. Without instruments, the outside is almost featureless. With instruments, the ship knows its velocity, orientation, thermal state, radiation environment, and position relative to local stars. The difference between sight and measurement is the difference between awe and knowledge. Cosmology had to become an instrument science before it could speak carefully about infinity. Human eyes saw a dark sky. Detectors measured a microwave background. Human intuition saw galaxies moving away through space. General relativity described expanding space. Human imagination pictured an edge. Topology offered finite spaces without boundaries. Instruments did not make the universe less strange. They made the strangeness harder to misuse. The inflationary record also brings us to the earliest limit of the episode. The CMB is old light, but not the oldest physical evidence. Before recombination, the universe was opaque to photons, yet it still left traces. Big Bang nucleosynthesis constrains the density of ordinary matter through the abundances of light elements. The primordial perturbation spectrum constrains early universe physics. Gravitational waves, if detected from the early universe, could open an older channel, though no confirmed primordial background has been measured. Neutrino backgrounds and other relics are predicted or constrained in various ways, but they do not currently give a simple map of total space. This matters because someone may ask whether we can see past the CMB by using something other than light. In principle, other messengers can reach earlier times. In practice, none currently provides a direct measurement of the global size of the universe. Earlier evidence helps test the model. It does not let us stand outside the horizon. The file then turns to the concept of a lower limit. If the universe is finite, how large must it be? Observations can place limits under assumptions. Curvature constraints imply that if space is positively curved in the simplest closed model, the curvature radius is large. Topology searches imply that if space has certain compact topologies, their fundamental domains must be large enough to avoid the detected signatures. Bayesian model comparisons can assign probabilities under chosen priors, but there is no single model-independent minimum size for every possible finite universe that the episode can honestly state as final. This is another place to avoid false neatness. It is tempting to say the universe must be at least some impressive number of times larger than the observable universe. Some papers estimate lower bounds under particular assumptions. Those are useful, but they should be tied to the models that produce them. The safest narration is qualitative unless the final source set includes a precise bound. We want to explain carefully. We can say the data show no evidence of a small universe repeating within the observable horizon, and curvature constraints imply any curvature radius is very large compared with the observable region. We should not present one number as the size of the whole. The ship's cartography table is good for this uncertainty. It can display a map with a known inner circle and several possible extensions beyond it. In one extension, the grid continues forever. In another, it curves back after a vast distance. In another, it repeats through a compact topology, whose scale is too large to fit inside the current projection. The inner map is identical in all three. That image captures the scientific situation without overstating the answer. The next pages are philosophical only in the sense that all measurement eventually becomes philosophical when it reaches its limit. George Ellis and other cosmologists have written about the special difficulty of cosmology. The universe is a single object, and we observe it from within. We cannot rerun it. We cannot compare it with many other universes. We cannot change its parameters experimentally. Cosmology is still a hard empirical science, but its empirical structure is different from a laboratory science. It relies on consistency across independent observations, on predictions, on relic signals, and on models whose assumptions are stated clearly. This should be part of the closing movement, not a detour. The episode's emotional weight comes from the fact that humanity did not fail to answer the question through laziness or lack of imagination. It pushed the available methods toward their natural boundary. It measured almost everything that could plausibly bear on the question: expansion, curvature, ancient light, galaxy clustering, topology signatures. What remained unknown for reasons built into the structure of observation. In the central chamber, I call up the evidence chain one final time. The first layer is light travel time. The universe has a finite age since the hot, dense early state, and light travels at a finite speed. This gives us a particle horizon. The second layer is expansion. Space has stretched while light travelled, so the present-day co-moving distance to the oldest observable matter is much larger than the light travel time in years. The third layer is opacity. The early universe was not transparent to ordinary light before recombination, so the CMB is a surface of last scattering, rather than a view all the way to the beginning. The fourth layer is geometry. The angular scale of CMB acoustic peaks and distance measurements from BAO constrain spatial curvature, and the result is close to flat. The fifth layer is topology. Finite spaces without edges are mathematically possible, and some would leave repeated patterns in the CMB. Searches have found no such signal for important tested cases. The sixth layer is theory. Inflation explains why our observable patch could be so uniform and flat, but it does not turn the unobservable whole into a measured object. I do not plan to present those layers as a list in the final reading voice. They are the bones beneath the paragraphs. The listener should feel them as a path, not as a checklist. The path begins with what reaches us, moves through how that evidence is measured, and ends with what remains beyond reach. The recovered file has a loose page near the back. It is not a scientific paper. It looks like a note written by someone who worked on a public explanation long before the networks went dark. The handwriting is hurried. Do not confuse the edge of evidence with the edge of existence. The sentence is underlined twice. I leave it in the file. The exterior observation airlock opens into a small viewing blister, a reinforced chamber with a wide pane facing away from the ship's main lights. I stand there for the final pass through the case. The stars are unevenly scattered, brighter in some directions, sparse in others, because the nearby universe is structured, and because the ship has its own location. The large-scale universe may be statistically homogeneous, but no local view ever feels perfectly average. We always begin somewhere. Somewhere is enough, if one is careful. From somewhere, humans measured the expansion of space. From somewhere, they detected the relic radiation of the early universe. From somewhere, they mapped anisotropies 1 part in 100,000. From somewhere, they inferred dark matter, dark energy, baryon density, neutrino constraints, curvature, and the acoustic history of the primordial plasma. From one planet, around one star, in one galaxy, they built an empirical model reaching across billions of light years. That achievement should not be made smaller because the final question remains open. A complete answer would have been satisfying. An honest boundary is more useful. The simplest current model, spatially flat lambda CDM with ordinary topology, allows an infinite universe. It fits a wide range of observations well. If one asks what model sits most naturally inside the standard framework, the answer is often a universe that is flat, homogeneous, isotropic on large scales, and spatially infinite. But if one asks whether infinity has been directly proven, the answer is no. The data are consistent with infinity. They do not compel it in a model-independent way. A finite universe is also not a single idea. Some finite models are ruled out or strongly constrained. A small, closed universe with obvious repeated CMB patterns is not what Planck saw. A universe with curvature large enough to shift the acoustic peaks significantly is not what the CMB and BAO show. A simple compact topology below certain scales is constrained by matched circle searches. The remaining finite possibilities are larger, subtler, or more dependent on assumptions. They survive not because they are favoured, but because the evidence cannot eliminate them all. There is a disciplined way to say this in the final script. The universe may be infinite. It may be finite and much larger than the observable universe. It may have a topology whose scale or form leaves no detectable signature in our sky. Current measurements make some possibilities unlikely and others unnecessary, but they do not transform the unobservable into the observed. The word no should be protected. Science knows through evidence. It can also infer, model, constrain, estimate, and prefer. These are not weaker words when used correctly. They are the grammar of honest measurement. I return to the office beneath the dome. The lamp is still on. Section labels from the archive are scattered across the desk as faint projections, slowly dimming. The folder has become thick now, swollen with the added packets from the vault and chamber. On the first page, the title remains unchanged. Is the universe infinite? What cosmology can actually measure? It looks less like a question waiting for a verdict, and more like a boundary marker placed with care. I turn to a clean page and begin the final case note. The universe we can observe is finite, not because space ends there, but because light has had a finite time to reach us through an expanding space-time. Its present-day co-moving radius is about 46 billion light-years. That number describes the reach of our observable region, not the measured radius of all that exists. The oldest light we observe directly is the cosmic microwave background, released when the universe became transparent. It is not an outer wall. It is an ancient surface in our past light cone. Its temperature and polarization patterns preserve a record of early density fluctuations, acoustic waves, and the geometry through which the light traveled. Those patterns, especially when combined with baryon acoustic oscillation measurements from galaxy surveys, show that the observable universe is very close to spatially flat. If there is curvature, it is small on the scales we can measure. The curvature radius would be large compared with the observable region. Flatness does not settle infinity. The simplest flat topology is infinite. Other flat topologies can be finite. General relativity describes local geometry. It does not choose the global topology by itself. Searches for cosmic topology have looked for repeated microwave patterns, especially matched circles on the CMB sky. Planck found no evidence for the tested compact topologies at scales where they should have appeared. That rules out some finite models. It does not prove that space is infinite. Inflation explains why our observable universe may appear so flat and uniform, and it suggests that the total universe could be far larger than what we observe. But inflation, as constrained by current data, does not give us a direct measurement of the whole. The final answer is therefore not a slogan. The best current evidence is consistent with an infinite universe and with the standard spatially flat model. It also leaves open finite possibilities that are too large, too subtle, or too weakly imprinted for current observations to exclude. The honest conclusion is that humanity measured the observable universe with extraordinary precision and found no edge, no strong curvature, and no confirmed repetition. It did not prove infinity. I stop writing there for a moment. The sentence has the clean feeling of a locked drawer. It gives nothing away that the evidence has not earned. Outside the dome, the stars remain scattered across the black. The ship's navigation system knows the coordinates of nearby catalogued objects, the velocities of local stars, the microwave dipole created by motion, the redshifts of galaxies stored in old surveys, the statistical ruler of BAO, the angular scale of the CMB peaks. The navigation system knows where it is within the observable file. It does not know the total universe. No surviving machine does. Still, the absence of total knowledge is not empty. It is structured by everything that was learned. We know why the observable universe is finite. We know why it is larger in co-moving distance than its age in light years. We know why the CMB surrounds us as an observational surface. We know why near flatness is measured through acoustic scales and distance relations. We know why topology can hide behind local geometry. We know why a negative matched circle search constrains some models and leaves others. We know why infinity cannot be verified by simply looking farther. That is the recovered shape of the case. A less careful archive would close with wonder alone. Wonder is present, but it is not enough. Wonder without measurement becomes decoration. Measurement without wonder becomes inventory. The old cosmologists had both, and the best records show the strain of holding them together. They could write equations for curvature and still understand that they were asking whether reality had an end. They could mask galactic dust from microwave maps and still feel the age of the light underneath. They could publish a non-detection and know that it mattered. The folder's final compartment contains no answer sheet. It contains a map whose central region is dense with annotation. The CMB sphere, the BAO scale, curvature contours, topology limits, inflation constraints. Around the annotated region, the page fades into unmarked paper. Not blank because nothing is there. Blank because the archive refuses to draw what the evidence has not reached. I seal the folder, then leave it on the desk instead of returning it to the vault. Some case files belong in storage when they are complete. This one belongs near the observation dome, where the glass reminds the mind what a horizon is. It is not a wall. It is where the present evidence stops. The universe may continue forever beyond that stop. It may curve or connect back on itself beyond any pattern we can see. It may be larger than every instrument, every survey, every inference humanity ever managed to build. The science does not give permission to pretend otherwise. It gives permission to say what is known with care. So the final line of the file remains restrained. Is the universe infinite? Possibly. What can cosmology actually measure? A vast observable region, ancient light, near-flat geometry, no detected small repeating topology, and a boundary beyond which the instruments become models. That boundary is not a failure. It is one of the most precise discoveries in the file. Humanity did not only learn facts about the universe, it learned the shape of its own reach. I lower the office lamp until the folder is lit by the dome alone. Above it, the star field continues in every visible direction. The eye wants to call that endless. The evidence asks for a quieter word, unbounded, perhaps, in the region we can test, unfinished in the archive, still open at the horizon.